Так, задержка, конечно, есть. Угу. Ну вот, это на нашем сайте. Все как бы работает.
Потом будем менять.
Ну, я в обед поменяю на следующую. Так, задержка, конечно, есть.
Ну, да.
Ну вот, это на нашем сайте. Все как бы работает.
Ну, я не понимаю, пока мы можем поставить куда-то.
Давайте пока вот этим примерно поставим. Ну, что вместо
этого?
Ну, то есть, как его подвигать. Что потяжелее, чем было. А если вот так вот бачку?
Нет, я просто...
Не, ну вот бачку.
Лапочку?
Да, так.
Ну, тут если не светлого, нет?
Ну, могут, конечно.
Ну, будет видно только верхнюю половину. Так.
от точки примерно. Буду как ученый выглядеть. Да, как дерево. Без трубы.
Ну, желательно, потому что
будем отсекать. А камеру на меня не нужно сейчас.
ты можешь попасть в нее. Я не знаю, как мы.
Не, ну,
Вот смотри, она вот так стоит.
не, ну, так точка видно.
Если ты сделаешь шаг вправо, тебя тоже будет видно.
Я сделал шаг вправо.
Ничего нет.
Ну вот, да. Все,
Начнем? Сейчас. Запись.
нет, еще 6 минут.
Очень не работает.
Ну да, сложно.
Работает. Супер.
Да,
Переименуйтесь там. Руслан Сергеевна. Она сама по себе. Все. Нужно каждого
Ну, и наверное, если мы все вместе, наверное, докажется. Нет,
Доброе утро всем. Сегодня мы продолжаем. Значит, у нас будет небольшое изменение в программе. У нас завтра Сережа Нечаев не сможет выступить. Он сидит перед обедом. Поэтому мы во время доклада, наверное, сфотографируемся. Всем коллективно. Может быть, здесь тоже может на улице учить. Вот. И я правильно понимаю, что докладчики после обеда всех умеют говорить по-русски, да? Точно, докладно. Тоже по-русски, да? А вот я не знаю, у нас вот рядом с этим вот роллапом, может, здесь да, здесь темновато. Это можно выйти еще раз на улицу.
Просто тоже
дождик обещают. Почти будет выходить на улицу.
я не предсказуемо. А видимо будет ливень большой, и все двигается.
Ну, у нас Кира все это умеет делать, давайте Кира вас представим. Вот, значит, если что, она будет нас фотографировать, если никто держать не будет. С нами данными не держать не будет фотографии. Вот, поэтому, значит, она подумает, где лучше это сделать. Самое, чтобы люди были, ну и вот Ролан был.
Да, несколько вариантов, а там уже будем исходить из того, какие погодные условия нам предоставят.
Если есть какие-то идеи, пожалуйста. Нам поручено, например, сфотографировать отдельно каждого часть из школы. Поэтому нужно отчитаться в бухгалтерии фотографии. Я понял, что билетами не надо отчитываться, только фотографии.
Не, билет тоже.
Билет тоже надо.
Более того, нужно отчитаться, если за 3 дня, но желательно это сделать в первый день.
Да, еще на программе стоит, значит, 4 часа наблюдения открытия с целью в Санкт-Петербурге. Значит, сегодня 6 июля, через год начнется конгрессом. И, значит, с подачи Смирнова и всех других организаторов, значит, сегодня там открывают стеллу по приемке побора. Делал вот там треугольнички, там еще что-то. Вот. И предполагалось, что будет прямая трансляция этого, там, людьми важными. Вот. И на сайте МИДа лежит ссылка, но она на сайте Конгресса. На сайте Конгресса ничего нет. Будет ли реально что-нибудь? Предполагалось, что мы 4 часа посмотрим, полчаса. Но вот неизвестно как. Посмотрим. Ну да, и вот, значит, наше мероприятие приурочено тоже до открытия Конгресса, поэтому вот я когда-то не. Ну все, сегодня тогда пережив. Позже, что там?
Okay. So, hello everybody. We are starting our second day of the conference, and the first talk in the morning is by Dmitry Live from many institutions, Tomsk State University, as well as major one, and the title is Two Mass Invariance Quandles and the Homotopic Equivalence.
Thank you very much. It's a great pleasure for me to be in Tomsk. It's my first time. Very pleasant. But I have to make a talk. It is about two nodes, Homotopic Equation, and philosophically, it's the growth of dimension with respect to the one node, the traditional nodes, and the Yang-Baxter equation, which plays the role of algebraic structure in quantum node invariance. So, if we want to consider more dimensional object, more dimensional topology, the algebraic structure should be changed, and the first very natural pretender to this role is the homological tetrahedron equation. I will explain why and how it works. But this growth dimension is relevant to many other subjects of modern mathematics and mathematical physics, and one point in my talk will be about loop quantum gravity and the language of spin forms, and I will give some hints, some ideas how the methods of two nodes can be applied to the loop quantum gravity in its mathematical formulation. So here's some list of words of notions from mathematics and mathematical physics which are related to my talk, but I have stopped all of them already. So I will give some details about the mathematical background of my talk. We'll start with the Tetrahedron equation, which is already well known for the auditory. It is a 4-degree equation. Here I expressed the linear or matrix form of this equation. So phi here is the linear operator in the tensor cube of some finite dimensional vector space, and the indices here. The indices here correspond to the numbers of the line on this picture. So we have 6 lines, 6 edges of the tetrahedron, and all the vertices of the tetrahedron are marked by the free numbers of these lines, and the lines have orientation, and the order of the operators in this form correspond to the possibility to apply an operator to the tensor cube of the tensor product of the corresponding vector spaces. So, for example, in this picture, the first place to apply an operator is this one. So it's pi 3, 5, 6, and it is mimicked by the fact that all these lines are oriented in the same direction, and they come to this point for the first time. Then applying this operator, so it's some non-formal explanation, but we can imagine the discrete dynamics. So these lines, this arrow, pass through the points, and for the second time we can apply an operator phi 2, 4, 6 at this point, because after the first step the argument with V6 is ready to be applied by an operator phi, and then apply the operator phi 1, 4, 5, and 1, 5, 1, 2, 3, and it is the left side of the Tetrahedron equation. And the right side of this picture is the same configuration, but with the inverted order of planes, or can be realized as the cross. We take this place, the place with direction 1 to 4, and we make it go through the point 3, 5, 6, and obtain this one. And with the same choice of the direction of lines, the order of the operator we can apply is the inverse one. So the first time it is the operator phi 1, 2, 3, then phi 1, 4, 5, etc. So it's the right part of the equation. Okay, so it's a definition and some graphic explanation, some graphic way to remember, to recall this form. There are many famous solutions for this equation, and the first one, which dates by the 19th century, it is the electric solution for the Tetrahedron equation. It was known in a different form, but in fact, this rational transformation from 3 variables x, y, z to x1, y1, and z1 gives a solution of the homological equation, and it is related to the star triangle transformation in electrical circuit by this change of variables. Another very known solution for the tetrahedron equation is related to the Euler decomposition in the orthogonal group. So if we introduce the Euler angles by this form in two ways, it means that we consider these matrices in 2 orders, and it produces 2 set of Euler angles, and the fact is that the exchange between this set of Euler angles also solves the tetrahedron equation. So principally, it always related to some 3 decomposition problem, some exchange between three components of something. In this way, it is the three components of this vector space. Here it is the same thing, because we change three resistances of one circuit to 3 resistances of another one, and it is the step of the drop of the dimension with respect to the Yang-Baxter equation. which correspond to the decomposition into multiplier of something. Okay, by two nodes, I will mean an isotopic class of the embedding of the two spheres to the four-dimensional space, but it can be generalized. The very known examples of non-trivial two-node can be obtained by the Zeeman construction, which produce two surface by the rotation of the long knot with the rotation of this knot in the three-dimensional space, and the proportion of this rotation produce different non-trivial two nodes. The traditional way to work with two nodes is to consider the diagram. So some generic projection of the surface to some three-dimensional space, and the generic projection means that we obtain the singularity of these three types. So we can obtain an edge of double point, a triple point, and a Whitney point umbrella. And so the working tool in this field will be the graph of singular points of the diagram with some additional information of the order of two cells of leaves of two leaves of this diagram. So if we choose a projection, we know which leaf is upper and lower, and it is some additional information, some additional combinatorial information related to the diagram. There is an analog of the Rademeister moves, the list of Rademeister moves. It contains 7 moves. It was proposed by Rosman, so it's a list of Rosman moves. So it should be looked in. So all of them has important geometric meaning. So sometimes they produce a Whitney point. Sometimes they produce the triple points of the diagram, like in this case, for example. And the most important move in this list is the seventh one, which is the same as the homological equation in its graphical explanation with what I was start. So the theorem of Rosman says that the equivalent knotted surfaces, the two diagrams correspond to the equivalent knotted surfaces, even only if one can be transformed from another by a finite series of the moves from this list and the isotopy of the diagram in actual. So it's the key tool to start to construct invariants of two nodes. I need to say some words about spin forms. So it's another combinatorial geometric object, and it appears in the modern approach to quantum gravity. It's an open problem, and there is no, for example, there is no working paradigms in this field, but it is interesting. It is actively studied and produced some interesting mathematical problems. So from this point, one is interested by the following object. By the the principal idea of quantum loop gravity is the discretization of space. So if one considers the one consider some graph that's in place of the two surfaces, for example. and the dynamic of this graph can be represented by Bordian by borders. So that one considers the graph of more generic types, so the trivalent graphs, and the borders between them, also the specific types. So here I represented the generic singularity of this borders. So this point is the center of the tetrahedron. So here from the bottom graph is the star in our picture of star triangle transformation, and here is the triangle, and it is a bordism related to the star and the triangle, and it appears in additional singular point, which is the same as the center of the tetrahedron if we make a partition by the medial planes. So basically, so it's a 4-valent point, and it is we can see the borders with only such kind of points between 3 valent graphs. Sometimes it is called the quantum history, which represents the fact that it is a dynamic of the 3-valent graph, which represent the discretized two-space. So I will say something about evaluation of such forms, but for the moment I will tell you about some known classical results in the theory of two nodes invariants. Here is the definition of the quandle, but it is known because it was explained yesterday several times. There is a natural approach to calculate the cohomology of quandles, which is just a generalization of the cohomologies of groups. And here I represent I give the details of the cohomology theory used by Carter, Kamada, and Said in their works on two nodes invariants, but it is just traditional reduced cohomology of a quandle. Then to define an invariant, they solve the problem of coloring of two leaves of the diagram. So here is the diagram. In this picture, I express the cutted leaves, which are bottom. So the upper leaf cuts the bottom leaf. So it is represented by this picture. And in the triple point, we have two kind of cuttings. So this is the upper leaf, this is the bottom leaf, and this is the medium leaf, which is cut only once, and this leaf is cut twice. And so the principal point in definition of such invariance is to color the leaves of the diagram by an element of a quandle, but it is like in one node, so they correspond to the element of the fundamental group of the complement of this node, and we demand only the condition that this leaf is colored by this composition, this element of the quandle, and the coherence condition for the triple point is automatically fulfilled due to the axiom of the quandle. The three cycle with the values in the commutative group is defined by this equation. Three cycle of the quandle with values in A, so this relation. And Carter and colleagues, they consider the following statistical model, statistical in the sense that it is sum of some values related to the configuration, to the state of some configuration. So in this case, they start from the Boltzmann weights in the vertices of the diagram of the node, which is calculated with the help of some chosen Zika cycle and the sign of the point. So it is definition of the sign, but I'd like to go further. So there is some rigorous way to define sign of all ingredient of this natural logic, and after that, one calculates the sum over all admissible coloring of the leaves of the diagram of products of Boltzmann weights over all triple points of the diagram. So also it is some natural object. And the theorem of Carter and his colleagues says that this function is invariant with respect to all Rosman moves and hence provides an invariant of the node. Now I need to. So it's a classical result, and for by my opinion, it's an analog of the construction for one node. Nothing more, but we can see this here. So it's constructed with 3 cycles of quandle, and for one node, we should consider 2 cycles. So philosophically, it's the same. Now I will give some ideas on perpendicular way to construct invariants, but it's not such efficient like the approach of Carter and Theta. So we produce only quasi-invariants, so some statistical models which are invariant with respect to subset of Rosman. I'd like to go quicker. So for the moment, the definition of the Zika cycle of the tetrahedron complex is such function. Here there are indexed variables which are explained in this picture, which symbolize the process of coloring of 2 faces of the 4 cube. So it's a projection of the 4 cube, and one can apply the tetrahedron map, so solution of the tetrahedron equation, each time when we push 2 faces of this 4 cube to obtain another 3 faces of this 4 cube. Okay. Also, I'd like to say that there is some rigorous way to define the tetrahedron complex and the homology of which produce such definition of the co-cycles. And then, it is an example of the 3 co-cycle for the electric solution of the tetrahedron equation. And then we define another statistical model related to the diagrams of the node, which is related to the coloring of edges of this diagram, in contrast with the coloring of 2 faces of diagram in the approach of Carter and Theta. So it is the condition of coherence. So at each triple points, the colors of outgoing edges should be related to the colors of the incoming ones by phi, which is the solution of the tetrahedron equation. And then we define the partition function corresponding to chosen diagram, not a node, by a diagram. And so we need a solution for the tetrahedron equation and some co-cycle, 3 co-cycle of the tetrahedron complex. And we define some partition function which is also the sum over the set of admissible coloring of products over triple points, of values of tricycles, and there is some way to define all signs and some additional factor which compensate one of the Rosen moves. And the statement of Igor Kiripanov, Georgy Sharegin, and myself is the following one. This partition function is invariant with respect to the first, third, fifth, and seventh Rosen move, and for some particular choices of solutions of the tetrahedron equation and the cocycles, there is also an invariance with respect to the sixth move. But it's not all. It's not a complete set of Rosen moves, so you can say that it is a true invariant of nodes. Okay. Now I go to the spin forms, and there's a way to relate the complexes of such type with the borders within trivalent graphs, which I consider. So the first step is to consider the white and black coloring of the three cells of my diagrams. I don't like to go into the details. There are some topological obstacles sometimes, but let us consider the case. Then we can color all three cells into colors, and then so it's a neighborhood of my triple point of the diagram. And there are four black cubes, and I can see the partial dual to this configuration. So I place the vertices of my new object in the centers of the black cubes, and so in this way I obtain a tetrahedron. So for each triple point of the diagram, I obtain a four-valent point of spin form. Then the edges of my singular graph of the diagram correspond to the edges of this tetrahedron or to the two cells of the spin form. So the problem of coloring of edges of my diagram is the same problem for the two cells of the two form. It is the same configuration of intersection of singularities in this case. So, and the classical problem of evaluation of spin form is for example, the three coloring of two faces, and it means that at each edge with two faces, we need that the colors of these three faces be different. Here is one of the possible coloring of two faces in the neighborhood of the singular point of the spin form. So there are only three ones, three possible coloring of the two faces. So I'd like to show that this problem is governed by the same construction, the same statistical problem that I used to construct the quasi-invariance. So this condition can be represented by some metrics in the tensor cube of the three-dimensional space, which is just the identical operator on this tensor product with distinct indices and zero otherwise. So it is a way to codify the condition of different colors. Okay. In fact, this operator solves the homological tetrahedron equation for some obvious reasons. So it can be expressed by this formula. So it corresponds to the solution of the set theoretical version of the homological equation for the set z over 3z. And so two parts of the homological equation are just the identical operator multiplied by the square of this function, but it is symmetric, so it's the same function on the right and the left side. So the condition of the coloring of the three coloring of the two cells of this form is codified by this solution of the tetrahedron equation, and it is the same thing as to take the identical set theoretical solution of the tetrahedron equation and this Theta cycle of its tetrahedral complex, and the simple theorem says that the three coloring problem for the spin form is solved by the same statistical the same partition function for this solution, for the identical solution of the tetrahedron equation, and this Zika cycle of this complex for the dual 6-valent complex.
Any questions? Comments?
Почему аналогичное решение уравнения, оно было асимметрично. Y. Ну, почему так?
Он асимметричный.
Нет, ну до этого было написано там X это какая-то дробь, Z это какая-то дробь, а Y симметрическое решение. Там нет симметрии.
Он не симметричный.
If you change the variables, it will be more symmetric.
So I don't know why it's not symmetric.
Да, ну да. По-моему, все эти сопротивления, это не обязано быть симметрично. Там симметрия, если аргумент переставить, то и значение.
Да.
Нет, вопрос был, почему не симметрично?
Нет, она симметрична в правильных координатах. Она симметрична в правильных координатах.
Представляется значение.
Конечно. Но если ты заменишь, если ты симметричным выражением сделаешь несимметричную замену, оно перестанет.
Here.
Да, но это не симметричная замена симметричным выражением. Ну, потому что ты сделал симметричное выражение замену. Я вчера ее показывал, это нужно несимметрично их поменять.
In the sense that it is square root of some transformation, of some involution.
У тебя есть обычное симметрическое решение, электрическое решение?
Он не написан, но там.
Вот если вот в этом выражении сделать замену, которую я шаю в самом доске, получится вот это. Ничего не знаю. Вот. Если ты сделаешь здесь замену, вот она там написана, по сути, да, то получится вот. Но замена несимметричная, как получается.
А после замены вроде так же и останутся?
Нет, там будет одно выражение станет полиномом, а два других дробями. Да. Ну, одно станет полиномом.
А вот может сделать замену, вот как Иван делает графическую замену. И тогда, может быть, просто появится полиномом.
Но дело в том, что по большому счету это уже тропическая замена. В смысле, да, тропическая замена выше делает. Если тут сделать замену, а потом отбросить кубические члены, можно делать тропическую замену. Тогда будет преобразование численных решеток. Да. Ну, в более простой ситуации, вырождение ситуации. Как ее сделать тропическую замену до вырождения, я не знаю.
А если так, это тоже по-английски?
Давайте вернемся к английскому.
Suppose that we have solution to the tetrahedral equation. Is it possible to construct a solution for the Yanmax equation? Yes. Construct some projection with
Yes, if you talk about the vector version of the tetrahedron equation, it trace over one of the direction produce a solution of the unboxed equation.
No, but I speak about the
Theoretic. Yes, then you should consider something like the stable points of this method. It produces.
Even in this formula, you can see it. If you forget about the cubic terms, if y1 is just the sum of x plus z, then you get out of the locally unboxed the usual unboxed. The usually unboxed equation is a specialization of the parameters. Other questions? Well, thank you very much. We will start next to 11.
что у нас как Сереж. Сейчас, да.
Магента. Zika Tetrahedron.
Сам по себе уже сам начало хорошего размышления. Если мы получим, что мы начали.
Ну да, да, да.
Я думаю, я сегодня слышу.
А сейчас,
Все, сейчас я гоню на начало. Быстро, да,
ты там.
тут вот там просто.
Давайте начнем уже время.
Давай, без 20. Okay, we are continuing our program, and the next talk is by Valery Bardakov from Institute of Mathematics and Novosibirsk in many other places. And he will talk on Tetrahedral Equation and related algebraic systems. Only two places. One is of the Institute of Mathematics, and only two places. Okay, at first I would like to thank the organizers for invitation, for possibility to give a talk, possibility to listen interesting talks. Thank you. Today I will speak about tetrahedral equation and some algebraic system which relate with this equation. At first, definition. Yesterday, Henderson gave a definition of the Young-Baxter equation, and I briefly speak about this and introduce notation. The quantum Young-Baxter equation is equation of the following form. And problem to find the linear operator A, which acts from where V is a vector space, and it's X from where V tensor V to the V tensor V. And it must satisfy to this equation where R12 is a map operator which acts on this space and acts as on the first and the second component as R, and identity on the third component. R13 acts as R on the first and the third component, and identity on this component. And now we have this product in the opposite. This is one Young-Baxter equation. But you understand, if you take the vector space of big dimension, when it's difficult to find solution for this equation, you will have a long system. That's understandable how it's possible to prove. And Greenfield suggested to consider so-called set theoretical solutions for the Young-Baxter equation. In this case, we have X, its arbitrary set. And we consider a map A which acts from X cross X to X cross X, and this map must satisfy the similar equation. And in this case, if we have found this map, we will say that this map is called a Young-Baxter map, and the pair XR is called a solution for Young-Baxter equation, or totally a solution. For example, if we take arbitrary set X and the map P, which is permutation of component, then it's not difficult to check that it's a solution. What is connection between set theoretical solution and quantum solutions? Connection is the following. Suppose that we have found some solution for arbitrary set X. We can consider a vector space with the base X when you construct the solution for the quantum Young-Baxter equation. And now some definition which connect with the Young-Baxter map and with Young-Baxter equation. Young-Baxter map, it's the pair of maps, RL and R left and R right. And it's called left non-degenerate. Left non-degenerate. If the following map, here we fix the second component Y. It's a bijection on the set X, and the similar for the right map. And our map S R is called non-degenerate if it is left and right non-degenerate. And R is called square free if R of x is equal to V square for any element x. And now Young-Baxter equation connected with a so-called break equation. If we have found some operator which is solution for the Young-Baxter equation, when the following product P is a permutation of components gives a solution for the break equation. Break equation have the following form, and here S1, S2, this is the operation of this type. And with the break equation connects the break group Bn with on n strength is defined by the following form. We have a generator sigma 1, sigma 2, sigma n minus 1, and the following relation. This is the factor commutativity, and this is analog of break equation. And if we have found a solution for the Young-Baxter equation or solution for the break equation, when we can construct a representation of a break group Pn into the group of permutation of the set x in power n by the following. I don't know the answer on the following question. Is it possible to find a finite dimension vector space and find a solution for the break equation or for the Young-Baxter equation? It's more or less the same. Such that this representation is free. Of course, for n equal 3, you can take Brown representation, and this representation gives you a solution for this problem. But in general case, I don't know. On the other side, we know that the group Bn it's a linear group. It's possible to construct playful linear representation. But on the other side, Ivan Dynnikov constructed a bijective solution which defined on the z square. It's S is a solution for the break equation, and this solution gives a faithful representation for the break group in the group of permutation of this result. I think it's very interesting. And now we want to find some group which connect with the solution for the Young-Baxter equation similar to the solution for the break equation connects with the break group. And it's possible to give the following definition. For the Young-Baxter equation, we can define two groups. The first one is a virtual pure break group, VPN. This group is generated by the elements lambda ij, where I is not equal to j, and defined by the following relation. You can see that this relation looks like as the Young-Baxter equation. And this equation is a factor commutativity equation. And the second group is the flat virtual pure break group, FVPN. This group is generated by elements lambda ij, where I is less than j. Yesterday, Bogdan Chuzhinin gave the definition of this group, and for us, I use the same notation for the generators lambda ij, because in fact, FVPN is a subgroup of VPN, and there is an epimorphism of VPN to a flat FVPN. We have this thing. And in fact, it's attraction. And now we want to construct some higher analogs, define the Tetrahedral equation and simplex equation for arbitrary n. I explain how it's possible to write this equation. What is this problem? When we consider the Young-Baxter equation, this is equation of this form, it's possible to present this equation in the following form. You can forget about this part, and now we consider only triangle. In the vertices of this triangle, we have three operators, and we are going around these vertices and write the product of these operators. And if you are going in opposite direction, you write the, of course, the right hand side of this equation. And now
let us do the following thing. We want to introduce tetrahedron, map tetrahedron equation. Here I consider only so-called set theoretical solutions. Material life suggested consider the vector space, but now we can consider arbitrary set X, and it's need to construct the map I, which goes from X3 goes to X3, is a map for some set when the pair XR is a solution for the tetrahedron equation if the following equality holds in the set of maps from X6 to X6. This map, this equation has the following form. In this case, we say that R is tetrahedron map, and this pair is called a solution for the tetrahedron equation. Tetrahedron equation was defined by Zamolodchikov in this year. And now I want to explain how it's possible to write this equation. And also its higher analysis. Suppose that we have this triangle. We take the shift of indices. We add to number 3 for all indices. And we construct this triangle. Here we have element R4, 5, R6, 5, and R5, 6. And now we add the new vertices, it's not this in the place, and construct three lines which goes across the first vertices, second, and third. And we have the tetrahedron, and now we use the same idea. We are going around the vertices of this tetrahedron. Now we understand the order. At first we go in these vertices, and after this, the vertices for the triangle. And if we write this product in the opposite order, then we will have tetrahedral equation. Now, if you want to construct an equation for simplex, you can do the same thing. We add one more vertices, take the shift of indices, construct the line, and you can write the equation for the four simplices, and so on. Now we want to construct some group for any n-simplex equation, which is similar to the group of V, Pn, and Vpn, and Fvpn. I will do it only for tetrahedron equation. It's not difficult to generalize on the case on arbitrary n-simplex. For example, if we consider the group R, we will construct two types of group, Vpn capital and small, and the group F, Vpn capital and small, that are analogs of group virtual pure braid group and flat virtual pure braid group for the Young-Baxter equation. For example, the Vp3n, its group which corresponds to the tetrahedral equation, is generated by elements lambda ijk with 3 indices, where all indices are different, and this group satisfied by the following relation. First relation is the relation of tetrahedral relation. Second relation is factor mutativity. If all indices are different, then of course the elements are commutes. This is the first group, and the second group is FVP3n, is generated by elements mu ijk. In this case, I less than j, j less than k, and is defined by the similar relations. Now I denote these generators by other letters because I don't know is it true that this is subgroup of this trivial group. For example, the group FVP3n, third group FVP33 is infinite cyclic. This group, free group, and this also free group. And first interesting example is the group FVP36. The group what is generated by 20 elements and is defined by 10 commutativity relation. And now we have two
analogues of tetrahedron equations. Also, our people consider another, it's possible to write the n-simplex equation in another form. And this form considered in the papers of Puchko and Volkov, and they consider another form of n-simplex equation. And for example, in the case of tetrahedron equation, this equation has the following form. You can see that now we have only 4 indices instead of 6 indices in the previous case. And it corresponds that if you consider the tetrahedron, you take planes instead of a line. You have 4 planes, and you can write this equation. And we introduce the family of groups B and capital and small, what are called by group with n-simplex relations, and this group, in the case of n capital, is V equal to 1, is a free abelian group with n generators, and where group of 2 simplex is generated by element Aij, where I less than j, and the long relation have the form of the Young-Baxter equation, this equation of this form, and the Aij commutes with Ai prime j prime if they have no Humo index. It's not difficult to see that this group is isomorphic to the group of flat virtual pure breakthrough. But B3n is generated by elements of this form and has the form of tetrahedral relation, where these elements are commuted unless they have exactly 2 common indices. See, for the tetrahedron equation, we have some different type of group. And interesting to compare these groups. For example, here we have that the group B3, 3 means that we consider tetrahedron, 4 is the number of generators, and this group is the only group with undefined relations. But this defined relation is more or less understandable. It's not difficult to see that if we take another set of generators, then this group is isomorphic to the following group. It's the fundamental group of closed orientable surface of genus T. In general case, we can consider the groups of this form. We take n, it's n dimension simplex, and the number of generators is equal to n. When we have the group Gn, this group with undefined relation. And the structure of these groups more or less understandable. We can study this group, we can find normal form, and so on. Now it's interesting to find connection between the group B34, this is the simplest group what corresponds to the tetrahedron equation, and between the group FVP36, which also corresponds to tetrahedron, and the first non-trivial group. We have the following proposition. The group B34 is isomorphic to a subgroup of FVP36, and there is a retraction and epimorphism of this group to the group of group B34 to the group FVP36. Hence, in some sense, this group is more general. And now we want to study set theoretical solutions for the tetrahedral equation. It's not difficult to prove the following proposition. If we have a solution if we have set theoretical solution for the Young-Baxter equation, then we can construct a set theoretical solution for the tetrahedral equation. If R is a map which gives a solution for the Young-Baxter equation, then we can take the following pairs. X is our set X, and consider the map R, which the map X on the X cube, the following form. On the first, on the second component, this map X as R,
and identity on the field component. And here it's similar when these two maps give solution to the tetrahedron equation. We can lead any solution to the Young-Baxter equation to solution of the tetrahedron equation. On the other side, it's also possible to find solution of the other type. For the solution, therefore, we know the following class of solution for the Young-Baxter equation, and it's possible to prove the following proposition. Suppose that sigma rho and tau are free pairwise commute permutations on the set X. When the following map R, what is X by the following formula, gives a solution for the tetrahedron. And as a corollary of this proposition, we can define some solution for arbitrary group. Suppose that X some group with multiplication and A it's a fixed element. When for any integers numbers K, L, and M, the following map gives a solution for the tetrahedron equation. Here we multiply any element on the A in some power K. And if X is abelian group and A, B, C are fixed elements, then the following map, here we add to all components X, Y, Z with different elements, A, B, and C, then we have solution for tetrahedron equation. We have some classes of solution for the tetrahedron equation, and now I come back to the Young-Baxter equation and recall the definition of biquandle and the definition of quandle. The idea for introduction of this new algebraic system, quandles and biquandles, is the following. Suppose that we have a pair where R is the following R left and R right, gives a solution for the Young-Baxter equation. We can define a bigroupoid. Bigroupoid is a set with two binary operations. Binary, of course, algebraic operation. One operation is point, and the second is star. And this operation is defined by the following: X star Y is the left component of our map, and X point is the left component, and X star Y is the right component. And if XR is a non-degenerate square-free solution, then this algebraic system is called biquandle. Biquandle were introduced in the paper of Fent, Jordan Santana, and Kaufman for studying invariant for the virtual nodes. If we take the second operation, trivial product A X star Y is equal to X, when we will have a quandle algebraic system with one binary algebraic operation. And Matveev and Joyce studies this algebraic system. Joyce introduced the name of quandle, and in fact, we have found some solution for the Young-Baxter equation 10 years before the paper of Lincoln. We constructed the link and node invariant and introduced the quandle. Quandle is the set with one binary algebraic operation which satisfies three axioms. And these three axioms comes from the Rademacher rules for node diagram. And also we have the way in the opposite direction. Suppose that if we have a quandle, when the following pair is a non-degenerate square-free solution for the Young-Baxter equation, which we construct by the following. And now we want to introduce something similar for the tetrahedron equation. An algebraic system with one ternary algebraic operation is called biternary,
And algebraic system with k-ternary algebraic operation is called by k-ternoid. And suppose that we have x r is a solution for the tetrahedron equation. When r is a set of free maps, when we can define free ternary operation by the following natural definition. And it's interesting to find solution for the tetrahedral equation, and we can use the idea which we use with Timur Nasibulov and Mahender Singh. We introduce so-called verbal quantles and study their structure. By analogy, we can introduce verbal ternars or verbal k-ternoids, and suppose that W is a reduced word in free group free with free generators, and G be an arbitrary group. When the verbal ternar GW is a ternar with one ternary operation which is defined by the following. Also, it's possible to introduce a generalization. We can take arbitrary number of reduced words in free group F3, and G is an arbitrary group. When the verbal ternoid is defined by the following manner. G is a group, and now we have this word, and the algebraic operation is defined by the following. And we can formulate the following problem. Suppose we have arbitrary abelian group. What verbal ternoids we can construct using this group? And now suppose that we have three reduced words, Wi, where I is equal to 1, 2, 3, and G be an abelian group. Put that R, A, B, C is the following map, when it's possible to prove the following theorem. For G is abelian group, and alpha, beta, and gamma are integers. When the following family give a solution for the tetrahedron. You can see that with different maps, some of them it's non-invertible, some it's vertible, and you have this map. And we can formulate the following question. Suppose that G be a group, define and free ternoid on G, which give a solution for the tetrahedron equation. It's analog with question, it's analog for the group. In the case of group, if we have arbitrary group, we can take conjugation operation, method like talked about this, and we will have a quantum. Is it possible to do something similar here? And also, some people studied the solution for the tetrahedron equation, for example, in the papers of Kashaev, Sergeev, Kazipanov, Sharygin, Talalayev, Kuchkov, Kazakov. We can find some solution for the tetrahedron equation. And suppose that x r and y t are two solutions for the tetrahedron equation. See, here x and y is different set. How is it possible to compare this solution? What solution it's better, what it's not so good, and we can suggest the following approach to this question. We can take some group what corresponds to the tetrahedron equation. For example, the simplest group G4 is the group with 4 generators and one defining correlation. We can construct two representations. Representation in the G4 in the symmetry group of X6, here G4 to the symmetry group of Y6, and we can compare the kernels of this map. If the kernel of the first map is less than the kernel of the second, then we say that this representation is stronger than the second representation. Now we can formulate the following problem. Find an invertible solution for the tetrahedron equation, which gives a faithful representation for a group of this type, or maybe some other group of which corresponds to tetrahedron equation. Its result is analog of, it's interesting to find result, it's analog of result of Ivan. This is the last problem, and thank you for Are there any questions, comments?
So there is a way to compare solution.
Maybe you come forward, otherwise people can.
There is a way to compare solution of the tetrahedron equation, just to consider the homologies of the tetrahedral complex. Are they related to the question you have posed about the kernel of the representation?
Yes. Yes, it's interesting because it's interesting to compare these two approaches.
Other questions? Other comments?
So I have a question. Is it possible to ask here?
Oh, Mahender. Hi.
Hi. Hi, Valerie. How are you?
Oh, I am fine. Thank you. And you?
Yeah, so I have one question. So given a solution of the Yang-Baxter equation, people have defined what is the structure group of that solution.
Yes.
Right. Yeah.
And you
So,
suggest to introduce this analog for the tetrahedral equation.
yeah, and in fact, that structure group for quandles agree with the enveloping group. For example, if it is a not quandle, then the structure group is a not group.
Yes.
So perhaps one defining such a group might give some insights about solutions of tetrahedral equation.
Yes, Mahender, I think about this question, but it's ununderstandable what is relation in this group. You remember that in the case of Yang-Baxter equation, when you take enveloping group, you take the group with the following relation: x star y is equal to x point y, image under the action of Yang-Baxter equation. Formally
Right.
here, of course, you can write this relation, but I don't know is it interesting or not. And I don't understand connection because the main idea for introduction of enveloping group in the case of Yang-Baxter equation, it's for knot. If we take a knot, classical knots, find its quandle and its enveloping group, it's equal to group of this knot. But here I don't know this analog. Formally, we can define this group, but is it interesting?
Yeah, if there is any group which is associated to a solution and also coming as invariant of some geometric object, that might be a candidate. I don't know, so but something, because I think the motivation for these people to define structure group in this form is exactly that.
Yes, maybe it's interesting to see. Thank you.
Thank you for the interesting talk.
Oh, okay.
Okay, any other questions? Then we will have a coffee break now for the next 20 minutes and meet 11:30. Спасибо. Слушай, какие слайды разбираешь?
Извините, а вам подскажете, куда? А, спасибо. Да.
Hello, anybody there?
И поэтому передвинем, доклад Михаила будет во время отдельного снова.
Сейчас, а что при том, что мы поднимем, да?
Еще раз, да, мы просто поднимем.
То есть вот...
И доклад будет ставить.
Михаил Чудовский вместо...
Можно так. Тихо, видно. Hello.
Hello. Fine. Okay.
So,
Hello, Samuel. Welcome to Tomsk.
В камеру, войди в камеру.
okay. Can you hear me, everybody?
Смотри туда, смотри.
Нет, нам надо
Смотри туда.
Встань.
вот сюда.
Is that good?
Yes.
All right. So the next speaker in our conference is Daniel Lee, and he will talk about ternary quasigroups and invariance of classical links and surface links. You're welcome. To begin.
So you can you screen? Can you see my screen?
Yes.
Okay. Thank you for inviting me this great conference and give this opportunity. So today I'd like to talk about ternary quasigroups and some counting invariants of classical links and surface links. So here are contents of today's talks. First, I introduce some basic definitions of not theoretic ternary quasigroups, and then I explain how we color the oriented links and oriented surface links by using these ternary quasigroups. And finally, I introduce some special kind of ternary quasigroups, and using this, I'd like to introduce some invariant for unoriented classical links and surface links. So here are definitions of quasigroups. First, the ternary groupoid is a set X. equipped with the ternary operation T, in this talk we write the image of ABC under T like this, and denoted by X and the ternary operation T. Combinatorial ternary quasi-group is a ternary groupoid XT, such that for any quadruple ABCD of element of X satisfying ABCT equal D, specification of any three elements of the quadruple determines the remaining one uniquely. This is important thing. Or equivalently, we can define this ternary quasi-group like this: the equational ternary quasi-groups. This is a set X equipped with the ternary operation TLMR, satisfying the following pair of equations for all ABC in X. So first one is ABCT BLA, and this equation we change T and L, then we have this one. Okay, and similarly, these another two equations. We call these operations LMR, the left, middle, and right division. In the late, we can see where these equations comes. Okay, actually this is equivalent to this uniqueness. Okay. Each equational ternary quasi-group gives a combinatorial ternary quasi-groups, and conversely, each combinatorial ternary group gives equational ternary quasi-groups with the three additional ternary operations defined like this. Okay, assuming the ABCT equal D. Then we substitute this one is here. Then we obtain these axioms. A finitely ternary quasi-group with n element usually can be described by Latin cubes, which is n to the 3 array in which every element appears exactly once in every horizontal, vertical, and columns. So any Latin cube defines uniquely ternary quasi-groups. Latin cube for finite ternary group XT with n element is sometimes written as n matrices, so that each matrix gives the operation table of the second coordinate B and third coordinate C for a fixed first coordinate A in the ternary operation ABCT. Okay. Here are some examples. The X with the 4 elements 1, 2, 3, 4. Then in that case, these 4 matrices represent a ternary quasi-group with 4 elements. For example, 1, 2, 3, T is equal to 1. Actually, this one. The first coordinate is 1. So, first matrix. Then the second coordinate is this row, and third coordinate is this column. So, 1 is the image of this one. And similarly, 2, 3, 4, T is 4. Then not theoretic ternary quasi-group, simply KTQ, is a ternary quasi-group satisfying these two additional equations. Actually, this equation comes from these pictures. If we consider some crossing, that we color the three regions A, B, C like this, then the remaining region is determined by A, B, C by the ternary operation T. So this region is colored A, B, C, T. So with this convention, we consider flat flat third randomized moves, okay? This one. We put this region A, B, C, D. Then this region is colored by A, B, C, T from this convention. And then this region is colored by this one, and this region colored by this one. And similarly, we color these regions A, B, C, D. Then this region colored by this one, and this region is this one, and this region is this one. And compare the final stage. Then this should be equal to this one, okay? So this is this actions, and this one should be equal to this one. Then this is this one, fourth actions. Actually, the right side of the action 4, the respectively 5, is obtained from the left side of 4, respectively 5, by substitution C to the B, C, D, T, and the B is A, B with A, B, C, T. So this one. C is substituted by this one, B is substituted by this one. Here are some examples of not theoretical ternary quasi-groups. But I think I can skip these examples, okay? There are many examples. Now we consider the coloring of oriented link diagram. For our convenience, we consider only finite not theoretic ternary quasi-groups. The XT be a given finite KTQ, and let D be an oriented link diagram. Then KTQ coloring of D is assignment of element of X to the complementary regions of this link diagram D, satisfying these two rules at classical crossing, positive and negative crossings. So A, B, C, D is color of these four regions. Then at the positive crossing, this region is the action of A, B, C, okay? Then this is actually the action of the left division, and this is a right division, and this is the result of the middle division. And the negative crossing, we change the color of these two, okay? So this is D and this is B. And these two regions are same. So with this coloring convention, Librizidowski proved this theorem. The number of KTG colorings of oriented link diagram D that does not change under oriented randomized moves. As a consequence, it is invariant of the oriented link type represented by this diagram D. Here is a graphical proof. Actually, it is enough to prove this theorem. Each before and after or the randomized move, the coloring is uniquely determined when we fix the coloring of the outside of the considered randomized move. Okay, so the first move, this region is A, this region is B, then this two region is A, B. Then these three elements determined uniquely, this one actually following this coloring convention, positive crossing, then this is actually colored by this element. And similarly, given AB, the region coloring, then this region is colored uniquely by these two elements. And similarly, second randomized move is also this region is determined by these colors of three regions by the right division and in this case left division. And finally, oriented randomized move 3, we use these actions. These two actions. Then this coloring is uniquely determined. In particular, not theoretic ternary quasi-group with the same primary ternary operator and the middle division is equal. In this case, the ternary quasi-group is called the involuntary not theoretic ternary quasi-group. We have involuntary not theoretic ternary quasi-group X and D be an oriented flat link diagram, then IKTQ coloring, IKTQ means involuntary not theoretic ternary quasi-group of D is assignment of element of X to the regions of D with this rule. Then also we have this theorem. The number of IKTQ coloring of oriented flat link diagram does not change under the oriented flat randomized move. As a consequence, it is an invariant of the oriented flat link represented by D. KTQ of oriented link actually and DB oriented link diagram and the KTQD, the abstract of KTQ whose generators are corresponding to the regions of D and the relations correspond to crossing as in the above conventions. Actually, 1 over 4 equivalent regions is assigned to each crossing, so it is sufficient to take just one relation among the four relations. Then the isomorphism class that does not change under the oriented randomized move. Hence, it is an invariant of the oriented link type represented by this diagram D. We call this algebra the not theoretic ternary quasi-group of link L, and we use this notation. Therefore, KT's coloring of D can be understood as homomorphism from this algebra to this L. We denote that this notation the set of all KT's colorings of D, then actually the number of coloring is the cardinal of this homomorphism set. Now we move to the two-dimensional case. As you know, the surface link is just the closed surface smoothly embedded in four-dimensional space. And the connected surface link is sometimes called the surface knot. And two surface links L and L prime is equivalent if they are ambient isotopic. And also each component of Ki of the surface link is oriented, then L is called oriented surface link. Oriented surface link's equivalence is some orientation preserving homeomorphism H, and this homeomorphism preserves the orientation of each component, okay? There are many descriptions of this two-dimensional link, but in this talk we use marked graph diagram representations. Marked graph diagram is a link diagram, possibly with a four-valent rigid vertex decorated as saddle crossings by mark, like this. So these are examples of marked graph diagrams. Orientation of the marked graph diagram is a choice of orientation for each edge of D in such a way that every vertex in D receives a source sink orientation. Okay? Source sink orientation like this. Then a marked graph diagram is said to be orientable. It admits orientation, otherwise it is non-orientable. Actually, oriented marked graph diagram like this represent oriented surface links, and the unoriented marked graph diagram represent unoriented surface links. For an oriented marked graph diagram D, we consider two resolutions, L plus D, L minus D, which are the oriented link diagrams obtained from D by smoothing each marked vertex like this into two ways. So if we have this marked graph diagram, then L plus D is this and L minus D is this one. We call L minus D, L plus D negative and positive resolution of D. Then our marked graph diagram D is admissible if both resolutions are trivial link diagram. Then two admissible marked graph diagram present actually admissible marked graph diagram and define the surface links, and conversely for given surface links so we can take always admissible marked graph diagram representing the surface links. Here are schematic pictures of this one-to-one correspondence. Modulo sum equivalence here, okay? Here are ambient isotopy, and here are the Yoshikawa move equivalence. Now I will explain the next page. Actually, we have some surface links, then we consider hyperbolic splitting. Then the intersection is just a marked graph diagram by putting the some mark at each saddle point. They are how often the saddle point, the positive directions. And conversely, we have some marked graph diagram here. Then we first consider a banded link by attaching a band to each marked vertex graph. Then we can consider some cobordism with the intersection is this banded surface, and capping off this trivial boundary with a disk, that we get the surface links represented by this marked graph diagram. So for this correspondence, we have this theorem. Two admissible or oriented admissible marked graph diagram present equivalent surface lengths if and only if they are transformed into each other by a finite sequence of oriented Yoshikawa move. Unoriented case, we forget the orientation in these moves. So these are Yoshikawa moves. Define equivalence of a marked graph diagram. Xt be a finite KTG, let T be an oriented marked graph diagram, then KTG coloring of D is assignment of element of X to complementary regions satisfying the rule. At every crossing, we have this one. This is exactly the same convention as above. And the marked graph, marked vertex, we have this convention. These are the same and these are the same for any orientation. Then the number of KTG colorings of oriented marked graph diagram D does not change under the oriented Yoshikawa move. So it is invariant of oriented surface link type represented by D. So these are main part of these talks. Unoriented not theoretic ternary quasi-group is a not theoretic ternary quasi-group satisfying the following additional condition. These three additional conditions for all A, B, C, X. Actually, there are two unoriented this kind of ternary quasi-groups of order 2. Just the 2. In the order 3 case, there are 4 distinct UKTG up to isomorphism. XT be a finite UKTG and D be an unoriented link diagram or unoriented marked graph diagram, then UKTG coloring of D is assignment of element of X to the regions of D satisfying these conventions. Then we have proved this theorem. The number of UKTG colorings of unoriented link diagram and the marked graph diagram D does not change under unoriented Rademacher move and unoriented Yoshikawa moves respectively. As a consequence, it is invariant of the corresponding unoriented link type represented by this diagram D. Here are graphical proof. The Rademacher move case, it is easy. So as in the classical case, as above in oriented case, I mean, these regions are uniquely determined by the colors of other three regions. Okay, and move 2 is also. And the invariance of the randomized move 3 comes from the ternary, the actions of ternary quasi-groups. You can see easily. And false move case, we have this colorings. Actually, we take these two colorings like this, okay, and C. Then this region is determined by these three colorings. The say D, actually A, B, C, D, T. Then this coloring determined uniquely the colorings of all regions of this move. Here, actually, DCBT, this region is colored by this one, but this one by using these actions, actually. These actions. So we see that this region is A. So the same color. And similarly, this color is the same. These colors are the same, okay, by using the actions. The move 5 is clear. And similarly, the 6th move is clear. Okay, these two color determined this one like this, and the 7th move is also trivial. But the 8th move, we color these regions A, B like this, and CB like this. Then same type here. Then the new regions are D, E, F, Z, and we color H, I, J, K. Then we can compute like this, but by using the actions in this way. Then we can E is equal to C, F is A, G equal B. Now these are all the same. So this gives a proof of the theorem. Here is some computational examples. Actually, we use these four. UT, the unoriented not theoretical quasi-groups. Then we compute our UKTG coloring numbers for unoriented surface link diagrams. Here, these are the Yoshikawa table of the surface links with the CH index of 10. That's we compute the coloring numbers by using these four algebra. Then we obtained this table. Actually, some are the same or some are distinguished by this invariant. You can see. Okay, this is the end of my talk. Thank you for your attention.
I see there is a question.
Yeah, may I ask one question?
Yeah.
Yeah, Professor Lee, thanks for the talk. So I have one question. So the construction of these ternary quasi-groups while constructing invariant seems quite similar to quandles. So I'm just wondering whether there is, So I'm wondering whether there is any relation between this quandle coloring invariant and the ternary quasi-group coloring invariant.
You mean the quandle coloring invariant?
Yeah,
Yes, recent paper by Sam Nelson and Oshiro, some other two persons gave some local biquandles.
Okay.
And yeah, the local biquandles is closely related to this kind of algebra. Actually, there are some homological invariant similar to the quandle cocycle invariant also developed by using this algebra. Yeah.
Oh, I see. So, okay. So you mean the cohomology for these algebraic systems is there in place?
Yeah, sure.
Okay, okay. And that recovers this coloring invariant. That should, right?
Yes, sure. Yeah.
Okay. Thank you.
There is one more question in the chat for you, I believe.
Yeah. Questions?
There is one more question in the chat for you. If you open
Chat.
Yeah, in the chat.
So which chat? What chat? This one?
In Zoom, there is a chat. I don't know.
I'm sorry. What chat do you mean?
Maybe you can announce.
Yes. Maybe the person who asked the question can do it in the traditional way.
Thank you for your very interesting talk.
Okay.
I want to notice a book by Wu, not theory and statistical mechanics, where he builds different invariants by statistical mechanics. In particular, he builds invariants by coloring diagram region as you do by very similar manner. And my question: have you found such specialization of your construction which specialized on interesting physical models? And have you compare your work with works? Thank you.
Actually, there are some echoes of the voices, so I can hear the correctly.
Yeah,
so,
if you like, can I read the question for you? It's written on the chat box.
Yeah.
Okay, so the question is as follows. I want to notice the work by Wu, knot theory and statistical mechanics, where he builds different knot invariants using ideas from statistical mechanics. So is there any, how have you found?
Yes. That's a good question. Actually, this algebra comes from the physical motivation. I introduced these actions, okay? These actions. Actually, these actions, these are three particles here. Then this is a vacuum region. Then these three particles moving some time. Then the vacuum states are changed. So after some passing the time, then we have this state, the same state. Then actually this kind of theory gives a Yang-Baxter equation in statistical mechanics, you know. So this is just some motivation of this algebra, I think. This is closely related to right-Milestone move in knot theory.
Okay.
Yeah.
Are there any other questions or comments? Right, if not, then we probably can proceed straight to the next talk. Yeah, oh, I'm sorry. Let us change the speaker.
Thank you for your attention again.
Thank you for the talk. So let us proceed to the next talk and stick to the schedule. Is that a good idea? So then, I mean, of course, providing that the next speaker is ready. Madeti, are you ready?
Yeah, I'm ready.
Oh, very good. So the next speaker is Madeti Prabhakar, I'm sorry, and he will talk about the Gardonian complex of theta curves.
Yeah, I think Professor Lee needs to stop the sharing.
Yeah. Stop. Yes.
So before he completes the process, let me thank the organizers and speakers and also the participants and also the organizers for giving this opportunity. Let me see how. Yeah. Is my screen visible to all? Sorry, there is some issue.
Yes, I see.
But I am unable to see my screen. 1 second. Yeah. Is it visible now?
Yes.
Is my screen visible? Okay.
Yes, I can see. Yes.
So, yeah, this talk is a joint work with my PhD student Satil Joshi. So this is the overview of my talk. I will be first giving a brief introduction to the spatial graph theory, and I will discuss what is Gaudian metric of a knot and Gaudian metric of a spatial graph, and then some of the known results about the Gaudian complex of knots. And then finally, I will discuss about the Gaudian complex of theta curves and some properties related to those and some results related to those. So similar to knots, the way we take embedding of knot in S3, S1 in S3, similarly we take a graph is an embedding of, a spatial graph is an embedding of a gamma in R3 or S3. So here is a simple example how we take a graph and its embedding. And in fact, for spatial graphs, there are many types of equivalences possible. In fact, Kobayashi had showed that there are 9 types of equivalences when we actually see the spatial graphs. But here I'm going to talk about only 2 specific type of one specific type of equivalence, that is ambient isotopic. So we say that 2 spatial graphs are ambient isotopic or equivalent if there exists an orientation preserving homeomorphism from R3 to R3, where the image of G1 is G2. So that is the equivalence that we will be talking about in spatial graphs. And similar to knots, the way we study knots by depicting them as the knot diagrams, and we will be studying the knots. So similarly here also, for spatial graphs, we take the regular projection of the spatial graph in R2 by retaining the information about the under or crossing strands at all the double points. And then we study the spatial graph diagrams. Here are simple examples of our embeddings of some of the graphs. So bokeh graph, handcuff graph, embedding of handcuff graph. Of course, I will be more interested in this particular type of embeddings, that is theta graph embeddings. Okay, so the way now we have diagrams. So obviously for theta diagrams, the equivalence, in fact, in a spatial graph diagram, the equivalence can be done by using the similar type of moves, which are Reed-Mister moves. Here we call it as Reed-Mister moves for spatial graphs, whereas the first 3 Reed-Mister moves are similar to the knots, whereas the other 2 moves, 4th move and 5th move, are vertex moves. So Kaufman had proved that two spatial graphs are ambient isotopic or equivalent if and only if you can convert one diagram to the other diagram by applying a finite number of these 5 reduced modes. When I'm talking about the spatial theta curves, obviously the fifth move will be much simpler. It will be, I can even consider it like this, which is equivalent to this type of move, sorry. This type of move. Or even I can do it like this, means this can be also considered as this equivalent as this one. So even for the fifth move also one can see if I'm restricting it to spatial theta curves, there won't be that many strands. So here is a simple example of considering some two theta graphs, diagrams, theta spatial graph diagrams, and showing that they are equivalent by using these 5 radial moves. I will be interested in some of the invariants which I will be using in this particular talk. So there are, even though there are many invariants for spatial graphs, I'll be interested in these two type of invariants. One is also known as constituent nodes, and the other one is the unlotting number for spatial graphs. And for, of course, there are many other famous invariants like Alexander polynomial, Yamada polynomial, and some algebraic invariants like the fundamental group, the topological symmetric group, and the fundamental quandles for the spatial graphs. So what I mean by unlotting number, in fact, Kawauchi had provided these unlotting numbers for any general graph, but here we are restricting it to only the planar graphs. So if I'm considering the planar graph embeddings, then crossing change operation turns out to be an unlotting operation. So here, the way we define in knots is similarly we define the unlotting number here. The unlotting number of a spatial graph is defined as the minimum number of crossing changes needed to transform a diagram into an unknot diagram. Unknot diagram here means the graph that we are considering in the beginning. That is the gamma graph. Okay, if you be able to convert it to that one, and then we can say that that is the trivial. So here is an example of a handcuff graph which is termed as 6-1. By making this particular crossing change of the star mark, this, and by applying the read-mixture moves, one can see that this can be converted to the handcuff graph, which is in fact this particular graph is the embedding of the handcuff graph. Therefore, I can see the unlotting number of this particular spatial graph 6-1 is 1. In fact, Litherland and Maurici had given a list of these prime theta curves up to 7 crossings. In fact, I'm able to provide only up to not complete 6. In fact, there are 16 6 crossing knots and 75 7 crossing knots are there. But here I'm providing, because of the space constraint, I provided only up to 611. So in fact, this Buck and O'Donnell had given even unlotting numbers for all the knots provided by Litherland and Maurici in their knot table, in the spatial graph table. So these pink colors are indicating that that is the place where you need to make the crossing change to convert that into a trivial one. Okay, so there are different type of connected sums possible if you consider the theta curves, but I will be interested to specifically talk about this particular type of connected sum, which is known as the order 3 vertex connect sum. So how we define this order 3 vertex connect sum? If you take any two theta curves, then order 3 vertex connect sum can be defined it like this by removing a small ball. Let me say this is E1, E2, and E3, and you take this vertex to be V1 and this to be V2. Same, label this as E1, E2, E3. Then by removing that ball, you connect it that E1 to E1 and E2 to E2 and E3 to E3. So you'll get a connected sum. That is, we call it as the order 3 vertex connect sum of two spatial theta curves. Okay. So other invariant that I will be interested is this constituent nodes. If you consider a theta embedding, then I can see that there are three constituent knots possible for every theta embeddings that can be represented by this V1, EI, V2, EJ, V1, where EI and EJ, I and J will be lying between 1 and 3. So for example, here I had given one specific embedding of a theta graph. If you look at this graph, there are three types of constituent knots possible. For this particular example, I can see that K12, K13, and K23, which turns out to be T of 2, 5, figure 8 knot, and trefoil knot. So these are the three constituent knots possible for this particular theta embedding. How these constituent knots will be helpful is one simple thing I can say. If one of these constituent knots turns out to be non-trivial knot, then immediately I can say that this particular theta embedding is a non-trivial theta embedding. Okay. In fact, this set of constituent knots turns out to be an invariant for that particular theta special theta graph. And also it also enables us to distinguish theta curves using invariants of knots. Now we have the constituent knots. So for these constituent knots, you can have a different type of invariants possible for the knots. So one can apply those knots for these constituent knots and check whether they will be same or not for different theta embeddings. So that way also we can distinguish these theta curves. Of course, even though it is one of the strongest invariants, still it fails to prove some of the very basic properties. Like for example, if I am considering Kinoshita's theta curve, to establish that Kinoshita theta curve is non-trivial, this particular constituent knot invariant is not going to help much. Maybe by looking at this particular example, you can see that this Kinoshita theta curve, for that, the constituent knots are all trivial. All the three knots are trivial. Therefore, it is not possible to establish from this constituent knot to say that Kinoshita's theta curve is a trivial. Okay, even though it is a trivial graph. So these are the invariants that I will be concentrating, and I will be using them in my further proofs. So first, let me define what I mean by Gaudian metric for knots. So in fact, for any unknotting operation, if you be able to take, one can define the Gaudian distance. But here Murakami had given this Gaudian distance using this unknotting operation, which is the crossing change operation. So here he defined the Gaudian distance between two knots, K and K dash, is the minimum number of crossing changes needed to deform a diagram of K into a diagram of K dash, where this minimum is taken over all the diagrams of K, from which one can obtain the diagrams of K dash. Okay, that is how we defined it. So one thing one can clearly observe is that this Gaudian distance turns out to be a metric on the set of knots with this particular operation. Okay, and of course it characterizes differences between two knots in terms of local transformations of the diagrams. And one of the lower bound that I can check is the Gaudian distance between any two knots is in fact greater than or equal to half of the difference between their signatures. Okay, that is one of the lower bounds. So once we have the lower bound, it is much easier to actually calculate the exact values. For example, the Darcy and Summers had given this Gaudian distance table for many knots. Okay. So similarly, the way we define Gaudian distance for knots, we will also define Gaudian distance for spatial theta curves. I will be concentrating on theta curves. Okay, so the way we are defining for knots, here also we take the minimum number of crossing changes that can convert a diagram of theta to a diagram of theta dash. Okay, where we are taking diagrams from the complete collection of this theta and theta dash. Okay. That is how we define this Gaudian distance. Now, one thing that I can observe is if I'm taking one of the spatial theta curve to be a trivial theta curve, then I can see the Gaudian distance between theta and this trivial is nothing but your unknotting number for the spatial theta curves, that particular theta. Okay, by using this particular property and the triangle inequality of the metric, one can see that the Gaudian distance between theta and theta dash is less than or equal to unknotting number of theta plus the unknotting number of theta dash. Okay. Now, Buck and Donald proved that this Gaudian distance between theta and trivial, that is nothing but your unknotting number. of that particular theta graph, that unnorting number is in fact greater than or equal to maximal constituent unnorting number. See, for this theta graph, we have 3 constituent nodes. If you be able to find out the unnorting numbers for these 3 constituent nodes and you take the maximum of all those unnorting numbers, then I can say that that particular number will be less than or equal to the unnorting number of that theta graph. Okay, so obviously the way we have a lower bound for Gaussian distance of nodes between 2 nodes, so how we can say what is the lower bound for the Gaussian distance between 2 spatial theta curves. So for that we have this particular result. So what is that? If theta and theta dash are 2 theta curves having constituent nodes, then I can say that the Gaussian distance between these 2 theta curves is nothing but is in fact greater than or equal to maximum of the Gaussian distance between their constituent nodes. Okay, the idea is very simple. If I'm taking n to be my Gaussian distance between 2 theta curves, what does that mean? That means that there exist some 2 diagrams, theta and theta dash of this capital theta and capital theta dash, such that by making n crossing changes, one can be converted to the other. So if you look at if D12, D13, D23 are the constituent nodes for theta, and D12 dash, D13 dash, and D23 dash are the constituent nodes for theta dash, then what I can see is you are making only n crossing changes among these to convert from theta to theta dash. Therefore, I can see that the Gaussian distance between the constituent nodes will be less than or equal to n, and hence in general I can say that this maximum of Gaussian distance between constituent nodes is less than or equal to Gaussian distance between these 2 theta curves. I want, of course, here also we provided a Gaussian distance between a few pair of theta curves. I specifically want all of you to remember this one particular Gaussian distance between 3,1 and 4,1 is 2. Okay, and in fact, for other where 3,1 star, which is nothing but the mirror image of 3,1, and 4,1 star is the mirror image of 4,1, then the Gaussian distance between 3,1 and between all these nodes are given here in this table. So one of the application or one simple observation that I can see is it possible for you to provide a natural number n, and for every natural number, is it possible to find out 2 theta curves whose Gaussian distance is exactly n? Okay, for that, of course, the proof is by construction. So if you are considering a theta n tilde like this with 2n plus 2 twists, then we know that the constituent nodes for this, one of the constituent nodes is nothing but t of 2, 2n plus 3 naught. Okay, now out of this 2n plus 2 half twists, if you make n crossing changes, it is easy to observe that this can be converted to 3,1. So what I can see is the Gaussian distance between theta n tilde and 3,1 will be less than or equal to n. But now by using this, the earlier result, that is the by lower bound, one can check that the Gaussian distance between theta n tilde and 3,1 is greater than or equal to the Gaussian distance between their constituent nodes. To be specific, I am considering this particular constituent node t of 2, 2n plus 3, and for this k 2, 3, then the Gaussian distance is nothing but is greater than or equal to half of the difference of their signatures, which in turns out to be exactly n. Therefore, I can see that the Gaussian distance between dg this theta n tilde and 3,1 is exactly equal to n. Okay, so now let me define what is meant by Gaussian complex of nodes. Hirasawa and Uchida had provided the Gaussian complex of nodes. In fact, it is a simplicial complex by taking the vertices of that particular simplicial complex as the nodes or isotopic classes of oriented nodes. And these n plus 1 vertices actually span an n space if and only if the Gaussian distance is exactly equal to 1. Okay, so here is a simple example of a 3 simplex by considering these 4 nodes. Their Gaussian distance is exactly equal to 1, where the star 1, star 1, star 3 are the places where you need to make the crossing changes to get the remaining nodes. So in fact, Hirasawa and Uchida proved that for any one simplex of Gaussian complex of nodes, there exists an infinitely high dimensional simplex sigma such that this one simplex is a subcomplex of this sigma. And further, he concluded that for any knot k naught, there exists an infinite family of knots k naught, k1, etc. kn, in fact, infinite collections such that the Gaussian distance is exactly equal to 1. To show the distinction between these knots, that they are distinct, these authors, Hirasawa and Uchita, utilize the quotient polynomial of the two-variable Jones polynomial of a knot, okay, which is denoted by k c n of k comma x. Using that, they are able to establish that these knots are actually distinct. Obviously, this type of questions will arise if I am considering different type of knotting operations on different type of knot classes. One question is, does there exist an n simplex spanned by n vertices of the Gaussian complex for every n belongs to capital N? And the other question is, for any m simplex sigma m of the Gaussian complex, does there exist an infinitely high dimensional simplex sigma such that sigma m is a subcomplex of sigma? As far as the knots are concerned, this particular case is true for m equal to 1. Okay, if you look at this result, for m equal to 1, Hirasawa and Uchida proved that one by considering the crossing change operation. Okay. Now, if one considers a CK move, in fact, Ohayama considered CK move and he provided the Gaussian complex of these knots, and he proved these two results, but for specifically for second question, for the case m equal to 0 and k greater than 2, he proved this particular result. And by considering virtual move and forbidden moves, Horiuchi and Ohayama proved for the case m equal to 0, and for h of n move, Zhang et al. Proved for the case m equal to 0 and this n greater than equal to 2. And Amnendra, myself, and Professor Andrew, we proved by considering the region crossing change and for classical knots and arc shift move for virtual knots. And for both the cases, we provided for m equal to 0. Case we provided these answers. Now, coming to the final topics, that is Gaussian complex of theta curves. The Gaussian complex of theta curve is also defined in a similar way because we are considering the crossing change as an unknotting operation. With respect to that, one can create a complex, Gaussian simplex, where the vertices are your unoriented theta curves. Here we are considering unoriented theta curves or isotopic classes of all the unoriented theta curves. And these n plus 1 vertices are nothing but your spatial theta graphs whose distance, Gaussian distance, is exactly equal to 1 with respect to the crossing change operation. Okay, so here is one simple example of a 3 simplex in theta curves. Okay, so of course I showed here the complete structure here. So if you make these crossing changes at 1, 3, and 2 for 7, 7, you will get different type of different knots that 0, 1, 3, 1, and 5, 2. And also for 5, 2, if you make these two crossing changes at 5, or either at 5 or 4, you will get 0, 1, and 3, 1 respectively, like that. Of course, one can show that they are equivalent to those knots by using the 5 redimensional moves for spatial graphs. So coming to the questions that we raised before, we would like to answer the similar type of questions for these spatial theta curves. Okay, so for any non-negative integer n, there exists a family of theta curves which spans an n simplex. Okay, so this proof is by construction. So I will be considering these theta curves like this, theta curve diagrams like this for any n. So I can show that the Gaussian distance between theta I and theta j is exactly equal to 1. First thing one I can observe is, suppose if I'm making a crossing change at any of these positions, then one can see that this one can remove, it is possible to remove this particular link, and then this whole thing will be removed. Then it turns out to be theta 1. If I'm considering theta I with I blocks and theta j with j blocks, by making a crossing change at star I plus 1th position, one can see that one can convert a theta j to theta I. Therefore, I can clearly see that the Gaussian distance between theta I and theta j is less than or equal to 1. To establish that it is exactly equal to 1, I need to establish that this theta I and theta j are actually different or distinct. To show that, I will be using these constituent nodes. Okay, so how we will do that? Let me consider the 3 constituent nodes of this particular theta graph, that theta spatial graph that I mentioned here. So for that, if you can see, the 3 spatial theta curves will be these 3. Okay, and out of these 3, you can observe that this also turns out to be trivial, and the second one is also trivial, where the third one I need to establish that this is a non-trivial one. To establish that this is non-trivial, I will be using the Jones polynomial. To be more specific, I will be using the degrees of the Jones polynomial. So of course, by using the scheme tree diagram for this kns, I can see that this vki of t, in fact, the maximum degree for vki of t turns out to be this 4I plus 1 for all I greater than equal to, and maximum degree of vk1 of t turns out to be 2. So with this, I can clearly tell that this ki's are different. Okay, so from that I can establish that this theta i's are in fact, this theta and theta j are distinct, and hence the Gaussian distance between them is exactly equal to 1. Okay, so this way we will be able to construct what is the Gaussian complex, simplicial complex for this particular theta graphs. Another question that will be there is, if I'm giving a the case where m equal to 0 case. So in a different way of writing, I will specifically say that if theta is any arbitrary vertex of the Gaussian complex, then I will be able to find an infinite family of theta curves where this theta also belongs to that family, and that family actually forms a Gaussian. This Gaussian distance is 1, and hence that forms an infinite simplicial complex, right? So the proof is very simple. I will be considering the constituent nodes of that whatever the theta graph given to me, and then I will take the 3 vertex connected sum between theta and the theta n which we formulated just before. Okay, this theta n's. Okay, so with that I will take the 3 vertex connected sum. Then what I can see is, if I'm taking a theta naught, okay, for n equal to 0, I can see that theta n dash is nothing but my theta only. Therefore, clearly I can see that theta naught dash, which is nothing but your theta, belongs to the family. Okay, and another thing that I would like to observe is the Gaussian distance between theta I and theta j. I know that by making only n crossing changes, it is equal to 1. By making 1 crossing change, it is actually the Gaussian distance is 1. So here also, if I'm making only 1 crossing change, I can convert a theta I to theta I dash to theta j dash. Therefore, I can see that Gaussian distance between theta I dash and theta j dash is in fact less than or equal to 1. Okay, so if I'm looking at their constituent nodes, 2 of them are trivial. If I'm looking at the non-trivial one, connected sum with kn, okay, which is a non-trivial one, then by looking at the Jones polynomial for the connected sums, I can see that this k23 connected sum with ki is not equal to k23 connected sum with kj. Therefore, and hence theta I dash and theta j dash are distinct. Therefore, they are equal to 1. So this proves the case for, in fact, what are the questions that I mentioned? For m equal to 0 case, we proved it for simplicial, this spatial theta curves, and of course, this is also we proved. Now, one question. Of course, there are many type of different open problems possible. So we have established for every 0 simplex of Gaussian complex of theta curves, there exists an infinitely high dimensional simplex sigma, such that this 0 simplex is a subsimplex of sigma. Now, is it possible to construct a 1 simplex? And of course, from here one can see that it may be possible, but of course, we can try this for different type of crossing change operations for the theta graphs. And another question will be, if suppose if theta and theta tilde with 2 theta curves whose Gaussian distance is 2. So is it possible for you to find an infinite family of theta curves whose Gaussian distance between this theta and star and theta tilde dash turns out to be equal to 1 for every n belongs to capital N. So in fact, this was proved by Bader in for knots case. So for any two knots k and k tilde of Gaussian distance 2, there exist infinitely many non-isotopic knots whose Gaussian distance to k and k tilde is exactly equal to 1. So when it comes to this particular case of theta curves, we are able to establish for a particular specific case or specific example, maybe I will say, when I'm considering theta to be 3,1 and theta tilde is 4,1. In fact, if you remember, I mentioned that the Gaussian distance between 3,1 and 4,1 is exactly equal to 2. Now, if I be able to construct this theta and star to be this particular collection like this, now by making a crossing change at C1 tilde, I can see that this will convert to a 4,1. And by making a crossing change at C1, I can see that this will convert to a 3,1. So the Gaussian distance between theta and star and 3,1 and theta and star and 4,1 is exactly equal to 1. So this gives a partial answer to this particular question, but in general, we would like to find out, is it possible for any case, any type of two knots given, is it possible, whose Gaussian distance is 2? Okay. So, of course, how we will show that they are distinct for n not equal to m, their constituent knots are not equal, which can be shown through this convex polynomial. Okay, that they are different. So this is what I would like to say about this. Again, these are the references.
Thank you very much.
Thank you. Thank you. I hope this is correct. Stay safe and stay healthy. Thank you.
Are there any questions? Comments, remarks, questions?
May I ask one question?
Yeah.
Yeah, so thanks, Prabhakar. So I have a question. So what is the global topology or of the space of this complex for theta curves? Can we comment anything on that? Or the homotopy type of, or the homotopy type of this complex, more precisely?
Okay. Oh, no, I'm not aware of that.
So you have this complex of theta curves, right? Yeah, with respect to Gaussian distance.
Yes.
So what is the homotopy type of this space?
See, essentially you will be getting one simplex means a line, and two simplex means then a triangle, and three simplex mean tetrahedron type of things, right? The type of structures you will get. So for that, if you would like to, one need to explore that. What type of structures that it can form. Of course, it is possible to check, but we did not check it.
Okay, thank you.
Other questions? Well, let us thank the speaker again. Thank you for your
Thank you.
The next talk is in 10 to 1, is 12:50, and Neha, are you online?
Yeah, I'm here.
Oh, very good.
Hello.
So we will meet in 6 minutes then.
Sure.
Thank you.
So is every talk in the afternoon going to be in Russian?
Yes.
Yes, yeah, sorry, yes.
Okay, because there are some talks that I was interested in, but
afternoon session. In the morning session. I'm sorry. Well, it is afternoon. Right? The last talk in the morning session is by Neha Nanda from Indian Institute of Science and Education and Research. And she will talk on Alexander and Markov theorems for virtual doodles.
Thank you. Am I audible?
Yes.
Okay. I would like to thank the organizers for giving me this opportunity to present our work. So today I'm going to talk about Alexander and Markov theorems for virtual doodles. This is work in collaboration with my PhD supervisor, Dr. Mahinder Singh. So before we begin, most of us are aware about the Alexander and Markov theorem for classical braids and links. This is done for virtual doodles, which I am going to define shortly. So in order to develop this Alexander-Markov description, we would require certain type of groups that play the role of classical braid groups. All these things we will discuss in this talk. So to begin with, I'm going to first define what are called doodles. They appeared in the work of Fenn and Taylor in 1979, who defined doodles on the two sphere as collection of Jordan curves without having any triple intersection point. Later on in the work of Kovanov, he extended the idea to immersed circle on a fixed closed-oriented surface. So for us, by a doodle, we mean a generic immersion of one-dimensional closed manifold on a fixed closed-oriented surface such that no triple or higher intersection points are allowed. So if we take a collection of all the doodles, we can define the notion of equivalence, and we can say that two doodles are equivalent if one can be obtained from the other by a finite sequence of local moves shown here. That is addition and deletion of monogon and bigon respectively. Here are a few examples of doodles on two-sphere. So we have one component and multi-component doodles. This is for reference. So before I proceed further, I'll take a pause here. So for doodles on two-sphere, we already know about the Alexander-Markov description. The role of groups has been played by twin groups, which has been studied in this context in the work of Kovanov, and also algebraic perspective of this of these groups have also been studied. Whereas this Alexander theorem was established in the work of Kovanov, whereas the Markov theorem was established in the work of Gotin. There is a theory of generalized knots and where the Markov theorems can be applied or not. It has been done in the work of Roger et al. So for our purpose, we are not going to dwell upon that. We'll now come to what are called doodles and surfaces, which was introduced by Bartholomew Fenn, Saichi Kamada, Naoki Kamada. For that, we first define what is called a representative of a doodle. By a representative of a doodle, we mean a pair F sigma consisting of the smooth map F from n disjoint circles to closed oriented surface such that this condition holds. So this condition essentially means that there are no triple or higher real intersection points. So the image of F on this sigma is called doodle diagram. So notice that we have considered smooth maps. So we are in a very nice setting. We do not want any wild intersections. We do not want infinite number of components. So we have a very good setting here to begin with. So here is an example of doodle, Kishino doodle on the surface of genus 2. This nomenclature is motivated by the Kishino knot that is proved to be non-trivial by various people. And it appears in virtual knot theory. So once we have the pair F sigma, what we do is we define an equivalence on the set of these doodle representatives. We say that two representatives are said to be equivalent if one can be obtained from the other by the equivalence generated by the following equivalence. The first is homeomorphic equivalence. That is that if we have pair F sigma and F prime sigma prime, so if we have a commutative figure of this sort, this essentially means that they're topologically same. Then next is homotopic equivalence. This means that, let's say we have a surface and we have a doodle diagram upon it. That is the image of two different maps, F and F prime. So if those are related to each other by these homotopic equivalent, by these local moves, then they are said to be homotopic equivalent. The next is surface surgery. So surface surgery involves finite sequence of addition and removal of handles disjoint from the doodle diagram. So by handle addition, we mean that first what we consider the surface, and we consider two disks upon the on the surface where the diagram does not appear, the image does not appear, and then we replace the interior and we replace it with an annulus by gluing the boundary of annulus to the boundary of two disks, which is shown here. And such one can show that this is indeed an equivalence relation, and such an equivalence class of doodle diagram is called doodle on a surface. Okay, so one thing I would like to comment here, we can see that there is variation between the surfaces in contrast to the definition given by Kovanov, where he did consider closed-oriented surface, but it was just a study on a fixed closed-oriented surface. So now we would like to establish Alexander and Markov theorem for these doodles and surfaces. But it is not natural and it is not easy for us to handle them. So what we are going to do is we are going to define some pictures or figures on the plane so that the entire information of these doodles, these figures on surfaces can be boiled down to the study of these diagrams on the plane. So for that, Bartholomew, Fenn, Kamada, they defined what are called virtual doodles. So a virtual doodle diagram is a generic immersion of closed one-dimensional manifold on the plane with finitely many real or virtual crossings, such that there are no triple or higher real intersection points. So we have two sort of crossings, where one is decorated by the small circle. This is a real crossing and this is virtual crossing. So here is an example of virtual doodle. So at the moment, it is just a mere graph. It looks like a graph where these are the vertices, where some vertices are decorated by a circle, but these are just not mere graphs. They captures the information of doodles and surfaces. So before that, we consider the notion of equivalence on these virtual doodle diagrams. We say that two virtual doodle diagrams are equivalent if they are related by a finite sequence of isotopies of the plane and the following local modes. So these are the modes. So these correspond to the real crossings. These correspond to the mixed virtual crossings. And this is the mixed relation. So note that we do not have this in the real setting, as in we do not have just real crossings, because that would, so this essentially means passing of this arc over this crossing. So if we have all these real crossings, then it would create a triple intersection, which we do not want. So we do not have such a crossing. But then this move, the mixed move, this allows us to go across this real crossing via the virtual crossings. So we still have the liberty to move around the crossings, but via virtual crossings. All right. So then it was proved by Bartholomew et al. That there is a bijection from the family of oriented or unoriented virtual doodles to the family of oriented or unoriented doodles on the surface. So by oriented virtual doodle, we mean the underlying orientation of the circles apparent. So here is one such example. So this doodle diagram has been taken on the torus, and this can be seen with through this diagram, which is a diagrammatic approach to this. All right. So once we have that, as I said earlier, that we would like to have groups that play the role of classical braid groups for our setting in order to establish the Alexander Markov description. So for that, we consider what are called virtual twin groups. They were defined in the work of Bardeko, Singh, and Vesnin in 2019, while they were studying the structural aspect of twin groups and pure twin groups. So it appeared as a generalization of the twin groups. I have not defined it formally, but for the sake of this talk, let's just assume it. So with generators, SIs and rho Is, SIs are, these are involutions having the following defining relations. So twin group is essentially a group with presentation SIs and these two relations. So these constitutes the relations of twin groups. These constitute the relations of the symmetric group. And here we have mixed relations. All right. Then there is a very prominent subgroup of these groups, which is called the pure virtual twin group, which is defined as the kernel of the natural surjection from VTN onto Sn. Right. So before I proceed further, I would also like to make a comment here. So in this talk, we are going to talk about the Alexander Markov theorem, but we have also studied these virtual twin groups and pure virtual twin groups in the algebraic setting. In particular, we have talked about the R infinity property, then automorphisms of pure virtual twin group, and etc. So, okay. So now in our work, we gave a topological interpretation of virtual twin groups. To begin with, we consider a set Qn of n points in R. So by a virtual twin diagram, we mean that it's a subset D of infinite strip consisting of n intervals, which are called strands, such that the boundary of this D are the n points on the upper boundary of the strip and the lower boundary of the strip, which satisfies the following condition. First is that the natural projection maps each strand homeomorphically onto the unit interval. This essentially means that the strands are monotonic. They are free falling. They cannot go back and come down. The second is that the set VD of all crossings of the diagram D consists of transverse double points of D, where each crossing has the pre-assigned information of being a real or a virtual crossing, shown like this. Okay, so then we consider two virtual twin diagrams on fixed number of strands, and we say that they are equivalent if one can be obtained from the other by a finite sequence of isotopies of the plane and the following local modes. And such an equivalence class is called a virtual twin. So one can consider the set of virtual twins, set of these equivalence classes on n strands, and one can, it is easy to see that it forms a group under the operation of concatenation. That is, that we take two virtual twins, keep one over the other, and then restrict the intervals from 0,2 to 0,1. So, and then we showed that this diagrammatic group of virtual twins is isomorphic to the abstract group VTN defined in the work of Bardeko, Singh, and Vesnin. All right. So then we proved that every oriented virtual doodle on the plane is equivalent to a closure of a virtual twin diagram. So this establishes the relation between virtual doodles on the plane and the virtual twins that we defined. So I will spend some time in giving a sketch of this proof. So for that, we first consider Gauss data. So this Gauss data for virtual doodles was given in the work of Bartholomew et al. So for by that, we mean it's for first we consider a virtual doodle diagram K, and then we define the Gauss data for this K to be the pair VRK XK. So let's define what are these. So VRK is the set of all real crossings of the virtual doodle diagram, and XK is defined as follows. So we consider a virtual doodle diagram, and then what we do is we consider each real crossing, and then we enclose it in these neighborhoods Ni, closed neighborhoods, and then WK is the complement of these neighborhoods in the plane. And then what to each, so and then we orient the diagram K. Does not matter how we orient it, we just want the existence of that. So once we have that, we see that this Ni intersects this real crossing at 4 points. So according to the orientation, we assign these symbols Cijs, so C1i, C2i, C3i, and C4i. And then V del K is the collection of all these symbols. So then we define Xk to be a tuple, to be collection of tuples from these symbols. So we have this AB belongs to the set Xk. If we have an arc in K intersection Wk, starting from A and ending at B. So we note that Wk has the arcs and the virtual crossings and also the circles. So one can, so this is how we define Xk. So this Gauss data is now this pair VRK Xk. And then we say that K and K prime have the same Gauss data if there is a bijection sigma from the real crossings of K to the real crossings of K prime, such that if AB belongs to Xk, that means that if there is an arc that connects A to B, then there should be an arc connecting sigma A to sigma B. So for concreteness, we consider sigma bar, which is induced from sigma like this. All right. So this was the, so we now we have this lemma that if K and K prime are two virtual doodle diagrams with same number of real crossings, then the following are equivalent. K and K prime have the same Gauss data with respect to bijection between their real crossings, and K and K prime are related by a finite sequence of VR1, VR2, VR3, and M moves modulo the isotopies of the plane. All right. So this lemma is crucial for us in the sense I'll explain shortly. So now next we define what are called closed virtual twin diagrams. So for that we consider the space R2 minus the interior. So we consider D to be the unit disk centered at origin, and then we remove the interior of the disk, and we define what are called closed virtual twin diagram. So we say that a closed virtual twin diagram of degree n, it is an oriented virtual doodle diagram satisfying the following condition, that K is contained in the complement of the interior of disk, and then if pi is the radial projection and K is the underlying immersion, then pi composed K should be an n-fold covering, where S1 is the boundary of the disk, and we assume it to be oriented counterclockwise. So maybe I can explain it with this example. So we have this disk and we have removed the interior. So we have this circle. Let's say it is oriented counterclockwise. So we have kept this D over here. And if we have a radial projection which emanates the rays from here, it says that each, the second point essentially means that if we emanate a ray from here, it should exactly cut this diagram at n number of points. For this example, 3 number of points. Then third axiom that we considered, the third hypothesis we considered was that it should be compatible with the orientation of S1, with the orientation of this boundary. So we can also take clockwise orientation, but for our convenience, we consider counterclockwise orientation. So if we have this, and the next point is that all these crossings lie at different levels. All right. So if we have this, then we call it a closed virtual twin diagram. All right. So in order to prove the Alexander theorem, what we are going to do is that we are going to so given a virtual doodle on the plane, we are going to construct a closed virtual twin diagram, because we know that once we have that, we can cut it at some level and we'll be able to get a virtual twin. And what are we going to do? By the use of that lemma that I stated earlier, we're going to produce this closed virtual twin diagram having the same Gauss data as that of the the doodle to begin with. So first, what we do is that we consider this virtual doodle. Let's say we are considering this. We give it some orientation. And once we have that, we are going to assign the symbolsCijs that I have done here. So once that has been done, so next what we do is that we are going to keep this in the downward direction like this. So C1, C1j, C2j, C3j, and C4k. And we see here that C22 is connected to C41. So C22 is connected to C41, which is here. So it so C22 is connected to C41. We can connect it like this, but then it would violate the orientation of this S1. So what we are going to do is that we are going to go around this circle and then join it like this in order to have the compatible orientation that we desire for. So so this is how we are going to connect the whole diagram. This is how we connect this in this thing. And whenever it cuts the arcs, we are going to give it a virtual crossing. So the way we have made this process, it is easy to see that these two have the same Gauss data. And once we have this, we cut it from here and then we get a virtual twin. So that is how we prove the Alexander theorem. Okay. So next we move on to the Markov theorem for virtual doodles. So we proved that, so right now we have that if we have a virtual doodle on the plane, we can have virtual twin whose closure is that virtual doodle. Sorry, I did not define a closure of a virtual twin. By a closure, we mean that we connect the ends of the virtual twin by non-intersecting arcs. So, so now we give a characterization. So the study of classes, equivalent classes of virtual doodles on the plane can be shifted to the study of Markov classes of the virtual twin diagrams on the plane. So so what are the Markov moves here? So we say that two virtual twin diagrams on the plane, possibly on different number of strands, they have equivalent closures if and only if they are related by a finite sequence of moves M0 to M5. So these are the defining relations. So one can check that if we close it. So the next is conjugation. This is right and left stabilization of real or virtual type and left stabilization of real type. So this is our right stabilization of real and virtual type. This is left stabilization of real and virtual type. So one can check that the left stabilization of virtual type can be obtained from the other modes. And notice that if we close these with these non-intersecting arcs, then we see that they are equivalent as virtual doodles. So one way is trivial. The second way is not so trivial. And another moves are, so next moves are right exchange and left exchange move. So these are right exchange, this is right exchange move and this is left exchange move. So it is easy to notice the one-way implication that if we close them, we get equivalent doodles. Now what we want to prove is that if we have two equivalent virtual doodles and corresponding virtual twins, then they are related by these sequences. All right. So for that, we proved the following critical lemmas. We cannot go to the proof of these lemmas, but I'm just going to give you a rough idea of how the proof goes. So we first proved that if we have two closed virtual twin diagrams, such that K prime is obtained from K by replacing the exterior of the real neighborhoods, that is K intersection WK by K prime intersection WK prime, then K and K prime are related by finite sequence of M0 and M2 moves. All right, and then we proved that more generally, we proved that if K and K prime are two closed virtual twin diagrams having the same Gauss data, then they are related by a finite sequence of M0 and M2 moves. All right. So next, what we do is that we consider. So we have two virtual doodles. By the sketch of the proof of Alexander theorem, we can find their corresponding closed virtual twin diagrams having the same Gauss theta. So then without loss of generality, we begin with considering two closed virtual twin diagrams. Since they're equivalent, there is a finite sequence of virtual doodle diagrams, say this, such that Ki can be obtained from Ki minus 1 from one of the local modes. So note that in between the process, we might not get closed virtual twin diagrams. It would just be virtual doodle diagram. So let's say, so for Ki minus 1 and Ki, we construct their corresponding closed virtual twin diagram, which are unique up to M0 and M2 modes. So now what we do is, let's say we are going to consider each move case by case, but for the time limit, I'm just going to consider the R1 move. So let's say that Ki minus 1 and Ki are related by R1 move. So we know that there would be a small neighborhood where there would be this Redomister move happening. So inside that local move, apart from that, we'll apply that braiding process and we are going to get the braid, the closed virtual twin diagram like this. All right. So once we have this, now what we need is, in order to make this as a closed virtual twin diagram, we have to pull this across. So we have to pull this across this circle here. So let's say we had that circle here. So in order to make this as a closed virtual twin diagram. So the problem here is that if I want to pull it across the circle, I may use real crossings or virtual crossings, anything of my convenience. So we also showed by a sequence of algebraic steps that no matter what kind of crossings we develop here and move here, it is going to be obtained by the sequence of M0 and to M5 moves. So in that way, we get these, and we know by the previous lemmas that they are related. Once we have this by previous lemma, we know that they are related by M0 and M2 moves. So since, this is the case of R1. Similarly, one can do for the rest of the cases, and that is how we got these modes. So we have established the fact that what all Markov moves are sufficient in order to classify the isotopic classes of virtual twins. So once we have this, so now we have an algebraic notion of studying these virtual doodles on the plane, and this also paves the path of constructing new invariants for these virtual doodles or doodles on surfaces through these Markov modes. Yeah, here are a few references of the comments that I made throughout the talk. So with this, I would like to conclude my talk. Thank you.
Thank you very much. Are there any questions, comments, remarks?
Thank you for interesting talk. I have the following question. You say that you can solve the problem for a virtual doodle group. Is it possible to solve conjugacy problem? If we want to use the Markov theorem to give classification for the virtual doodle, it's need to have solution for conjugacy problem. Is it possible to give us this solution?
Can you please repeat the question? Is it possible to?
Conjugacy problem for the virtual string group.
But I've not thought about it, but we'll have to see this. I don't know.
I don't. And
at the moment, I don't know.
Okay. And the Kishino doodle, is it trivial or not?
Kishino doodle is non-trivial.
Non-trivial. Who proved this?
So it was in the work of these, the Doodle, Doodle and Surfaces.
Yes. Okay, thank you. Any other questions? Any questions in the chat? Okay, so let us then thank the speaker again. And that we conclude our morning session, therefore, and continue at 3.